So given a metric space, we know how we can make and a subset of it, we can make this into a metric space by simply restricting the metric. Now we want to do something similar for topology, but you can't restrict a topology. Instead, you do something a little different. Suppose we have this set here. Remember, if this was a metric space, then we are looking at a ball in the larger metric space. And the ball in this subspace is simply the intersection of the subspace with the ball. Okay, and since these form a subbasis, one has a very natural definition, and which will satisfy both coincide with this what we did with metric spaces and will be nice in other respects, namely, so suppose we have X and omega is a topological space. Okay, and Y is contained in X. Okay, so you will let's describe omega Y as just being Y intersection open sets V in omega. And the following proposition is easy. Proposition is easy, which is that omega Y is a topology on Y. Yes, so of course the first thing is union. So if I took a union of sets of this form, so these depend on distributivity. Okay. So namely, we want to show it's a closure under union. Namely, if I look at union, alpha belongs to A of sets here, and these are sets Y intersection V alpha. Well, we have distributivity of intersection over union. So this is Y intersection union alpha in A of V alpha. And this is in omega Y. So if I took elements in omega Y and took their arbitrary union, then it would also be in omega Y. And intersection is, well, similar in a sense, but it doesn't involve distributivity. So suppose I took a bunch of elements here, that is I took Y intersection V1, intersection so and so, intersection Y intersection Vn. This is Y intersection these sets. And these are all open sets, that is to say, so Vn, all these are open. Each Vi, so I should clarify here, so each V here belongs to omega, and similarly each Vi belongs to omega. Well, so this is also in omega Y. And third property is that the empty set is phi intersection Y, and Y itself is phi intersection the whole space X. So these belong to open sets. Okay, so this is an example where you can take subspace topology. Okay, and so the second proposition, which follows straight from the definitions, is that if X is a metric space, the topology, we have two possible topologies on Y. The subspace topology on Y from the metric topology on X is the metric topology on Y. With respect to the restricted metric, with respect to dy, which is the restriction. So let me say x dx is a metric space. Okay, so I'm going to just declare this to be an exercise. There's no idea involved, it's just routine check, but it would be helpful to solve the other exercise also. So here is another exercise which is worth solving first before having these sets. So if B is a basis for omega, then let's write By in an obvious way. We look at Y intersection V, and the V belongs to B. This is a basis for omega Y. Okay, the proof is really just by, if I get rid of this picture here, this proof is really by, oh, it was maybe not get rid of the picture. Let's keep it. This is a basis for omega y. Yeah. So in this little corner, the idea of a proof is that exactly omega is the set is unions of alpha in A V alpha for collections V alpha in B. Okay, so and then omega y is y intersection union of alpha in A of V alpha for collections, such collections, which is nothing but the union over alpha in A of y intersection V alpha. Okay, so again we are using distributivity. I haven't spelt it out exactly what these collections are, but it's quite obvious. You look at subsets, open subsets, like these open balls, and we take a union of these. So in this case we could have had several of these sets, and we are looking at the union of these and intersect with y. It's the same as intersecting each of these with y and taking the unions. So we will exactly see that this basis is the basis. Okay, so the basis is the basis tells you that we need to really just work with the basis of the metric topology, and we know that, and it's obvious that the restriction of the ball is intersection. The ball in the restricted metric is the intersection of the ball. Okay, so these were some this was the definition of a subspace topology, and we have many examples where it actually just coincides with a given topology. Okay, there are just a couple of other things we have to see in generality about subspace topologies before we will start using them in the case of topological concepts, continuous functions, and so on. And what we should be clear about is inheritance and non-inheritance. Okay, so already you could see in that example, and which I will redraw, if I have this curve here, and let's say it's open at these ends. Okay, so maybe I'll make it a little more interesting. I'll put it dashed. So this boundary is not included. That's why it's dashed. So if let's look at a typical generic set here. This is not included. So this set will not be closed because the complement will include these boundary points, and every ball around them intersects this. So it is not open. So the complement is not open. Okay, so inheritance. So in general, if I look at V in Y, open in Y, this does not imply V open in X. So V is of course a subset of Y, which is a subset of X, so it's a subset of X. So here's an example. Here's an open interval. An open interval is open in this set, which is really the real line in disguise. I could make it a real line, but it's not open in the larger set, because if I take an arbitrarily small ball, it's not contained in Y. Okay, and you see the problem is Y itself is not open. So that's the positive statement we will write. But meanwhile, similarly, if I took a point here, which is this boundary is not in the set, but any ball around it intersects the set. So it's not in, so this set is not closed, and this point, yeah. So we will, even though the whole space has to be closed in itself by definition. Okay, so what we can conclude, so suppose we write A in contained in Y, closed in Y, does not imply A is closed in X. However, yeah, so first to clarify here, the example here is take the whole space. It's closed in itself, everything is closed in itself because its complement is the empty set, which is open, but it's not closed in the larger space R2. So X is R2 here, and so this is Y and X is R2 in this example. Okay. However, we have the following proposition. if, let's say, y in x is open and v contained in y is open in y, which means open in the subspace topology, then y is contained in x is open. Sorry, not y, but v contained in x is open. So open subsets of open subsets are open. And B is almost the same thing, but with closed subsets. But closed subsets of closed subsets. So if this is closed, and let's call it A in Y closed in Y, which means in the subspace topology, then V contained in Y is closed. For B, A is easy. For B, there is a more important property that I have not yet mentioned, which I will mention, which will give B like A. But first of all, to dispose of A, so V contained in Y is open in Y, which means, so by definition, so V is going to be Y intersection W, and W open in X. This is definition of the subspace topology, right? So its intersection, so set is open if it's an intersection like this. Okay, so what does this imply? So V is Y intersection W, but Y is open and W is open. And this is a finite intersection of open sets. So it implies that W is open. Okay, and B, like A, well, B is actually simpler than, we come back to the proof of B, but we use theorem below. And I'm calling this a theorem because it's important, but it's actually very easy. Theorem A contained in Y is closed in the subspace topology if and only if A equals Y intersection F for some F contained in X closed. So just as we get open sets from open sets, we get closed sets from closed sets. Okay, and so the proof is that A contained in Y is closed is equivalent to, of course, that Y minus A open, which is equivalent to there exists V in X open such that Y minus A is the same as Y intersection V. Okay, so the Y minus A has to be an open set. So now what is these? These are the points in A. So here is Y, and here is some set A. And Y minus A consists of points here and here. Those that are not in A, and those that are in. So here's Y, and Y minus A is Y intersection. So those points that are not in A, that are in Y, okay, so they are all in V, and so you can see that this is just equivalent to saying that A is equal to, or let me be specific, simply set equivalence will tell you this equation is nothing but A equals Y intersection the set X minus V. Okay, so just compare the points in these two. So this is, so if a point is in A, it's either in, well, it has to be in Y. Y is a subset of A, so it has to be in Y, and it also has to be in X. Of course, it is a subset of X, and not in V because of this equation. Okay, so any point in Y, A which is in Y and in V is not in A. And conversely, you can just check the set things. And of course, this guy is closed. And reverse this, any closed set can be written as the complement of an open set. And so we see that if a set is closed in, if an intersection of this form, A equals y intersection f. You write f as x minus v, and then you observe that the complement of A in y is just the intersection of the set V. So if f is equal to x minus v, then the complement of A in y minus A, is going to be y intersection v, and so that is open, and so A is closed in y. So this is a fully reversed argument. This tells you that subspace topology, we not only know the open sets, we also know the closed sets. Okay, and then we will see one more important fact about hereditary, but first let's dispose of this. So if y contained in x is closed and A is contained in y is closed in y, then V is contained in y is closed. Use theorem below, and then it becomes just like the previous one. Okay, A is contained in y is closed, implies A equals y intersection f, f closed, which implies of course A closed in x, because now this is an intersection of two closed sets. This is closed and this is closed. So because closed and open are closed, that is closed under the operation finite intersection, we see that if we take subspaces, then which are open, then open sets of that are open in y, and closed sets are closed in x. Okay, this is closely related to one more important property we see, which is really what inheritance is. And what is the inheritance we want? We want the following theorem. So suppose we have x as a space, and then y is contained in x. So y is a subspace of x, and suppose we have z contained in y. Then z has two topologies, right? So y is some creature like this, and then maybe z is something even smaller like this. Okay, it has a topology which comes straight from x, and it has a topology which comes from y, and y has a topology which comes from x. Okay, so then what we have is then the subspace topology on z from x and y with subspace topology. Coincide. Now this is easy, but if it didn't happen, everything would be a mess. So it is, that's why I've called it a theorem. So it makes it rather important for consistency. Otherwise we'd pass to a subspace and then pass to a subspace again, and the history of how we got there will matter, instead of saying that we are all looking at a bunch of subspaces of these. Okay, so what are the two subspaces? The two topologies. Well, one is directly from z, omega, let's call it zx. This is going to be equal to v intersection z, v contained in x open. Yeah. So along the way we've stopped using omega and just saying open here, is because by now one assumes everyone is used to this terminology, and omega zy is v intersection z, v open in y, but this by definition is v intersection z such that v equals w intersection z, w intersection y, w in x open. So we are using the subspace topology, and this is simply w intersection, we look at intersect with y and then z, and then w open in x. Yeah, so here it's open in x. So we simply substitute, instead of writing it as V intersection Z, V is this, so we substitute it, and it's ranging over all open subsets of X. But of course, Z is contained in Y, so this is just W intersection Y. W open in X. Okay, so this is an important thing. So we now have a nice notion of subspace topology. For metrics and hence for all our common examples, it coincides with what we expect. And we have nice hereditary properties and some are true, some are false, but where they're true, we know why they're true, and where they're false, we know why they're false. And crucially, this is consistent, because if we pass to a subspace and then pass further to a subspace, that is the same as passing directly in a single step.